Hi, and welcome to the demonstration portion of ESI Live 2024 Automotive. Hopefully you've had a chance to learn today not only about ICI-DO, but also the range of other ESI solutions, from virtual manufacturing to prove if the piece parts within a vehicle architecture is safe and manufacturable, vibroacoustics to validate if the vehicle concept is quiet enough on the inside to enchant your customers, while being audible enough outside to keep pedestrians and cyclists safe, and how ESI provides solutions that assure that an EV can keep us safe in case of accidents when it comes to structural strength and airbag deployment, but also drivable when crossing standing water, and that it has the range to take us where we want to go. In designing a new e-mobility product, decisions are made to include a battery of an intended kilowatt hours and number of and size of e-motors. These decisions cascade into constraints to product packaging that must be validated, hopefully before we take that concept to the auto shows and promise ranges and performance that just might not fit. Packaging decisions regarding the placement or content within the vehicle could have a negative impact on the performance of that vehicle in terms of vibroacoustics or liquids channeling and water intrusion prevention. Likewise, resolving issues with an EV's design and design for manufacturability or serviceability could accidentally block engineering intent for the drivetrain packaging and performance, or create issues for body manufacturing. With ICI-DO Weave, we provide a virtual time machine that allows stakeholders in engineering or process teams to experience the impact of yet-to-be-constructed assembly plants or service and maintenance environments to avoid that risk to the future vehicle programs and to the people who ultimately build, maintain, and operate the cars of tomorrow today. So let's take a look first at how ICI-DO Weave, when used to do individual engineering validations, could be used to validate things such as the length of and the shape of an individual wire harness. With ICI-DO Weave, enterprise users can choose to use ICI-DO Integrate to conduct individual design reviews. Take, for example, an engineer responsible for the release of the power distribution wire harness of this proposed EV. They use ICI-DO to sketch a cable route, or perhaps they imported that from CAD in the PLM system. With ICI-DO, they teleport themselves effectively from their desk to the future vehicle to test immediately if that cable proposal has sufficient length to reach the critical components. You see, digital transformation and the elimination of prototype development from many early milestones within vehicle development programs mean that oftentimes OEMs cannot validate that a harness will be installable or replaceable until much later in the vehicle program when pre-production parts are readily available. It's too late to cost-effectively adjust our plans and risks delay of that program if we have to wait until physical mock-ups. Being able to validate our decisions about cable length and route while still working in digital or virtual prototypes prevents any of those delays from being able to derail our program. ICI-DO Integrate allows engineers to mitigate that risk by powering virtual experiences without having to wait for the construction of physical prototypes and minimizing non-value-added data preparations and manipulations just to make VR happen. While performing that validation, the engineer might find that the cable length requires an adjustment to increase or perhaps decrease that length. They can modify the length of the wire harness and test that assumption right away within ICI-DO. There's no need to go back to CAD and import a new length, but instead we'll immediately suggest that new length and validate it, and that way take it back from ICI-DO to the CAD or PLM environment as a deliverable, confident that this new length will in fact improve vehicle design and packaging. Of course, there's plenty of other content within an EV besides just the battery and those wire harnesses. So take, for example, something as mundane as just a headlamp. And we might be considering how are we going to package that headlamp within the vehicle architecture. So in this case, we're looking at someone trying to plug a wire harness into a headlamp assembly on this particular vehicle. Now again, this is maybe a different engineer from a different team within that same vehicle program. And what they're trying to do right now is show that their hand could in fact fit underneath that part of the structure of the front end of the car to reach the harness. Now, if that's not possible, maybe they have to slide that headlamp out of the way and then plug it in before they install or finally bolt in that headlamp. And we saw in this case, the cable still wasn't the right length. So again, increase the length of that wire harness by editing it within ESI Do Integrate and see if that new length wire harness will be more accessible, more installable. So in fact, we do see there's enough space here for a human hand as well as getting that wire harness installed without pinching. And we are validating that just by using ESI Do Integrate, and in this case, we brought in a CAD model of a 95th percentile male hand to make sure there is sufficient fit. Now also, if we want to go a little bit further, here you can see one of my colleagues using ESI Do with a tracked real headlamp. So maybe that's the real headlamp from a past production vehicle, and they've mounted on it a tracker to give them the weight and the feel of what it would feel like to mount that headlamp inside of the vehicle structure. And if she determines that that was a plausible or implausible process, we can just have other people join into the VR session and similarly grab that headlamp and see if they agree that this is an easy to install, easy to replace headlamp, or do we want to modify anything about the design to make it easier? There are countless opportunities and requirements to make sure that the individual components have sufficient space and sufficient clearance with their adjacent componentry and the rest of the structure of the vehicle. So here you can see just a number of teams going through and validating, do these individual components suit the assembly or disassembly within that vehicle structure well? Now we can do that as individuals, or in the case of this video, we can do this collaboratively. So here we can see 3 engineers all sitting in different locations and working perhaps from home or their remote offices, and they're validating what the assembly cell would have to be for yet another component to be installed on this vehicle. So in this case, it's a trailer hitch. And we want to validate that the proposed tooling for the manufacturing plant and the assembly of that hitch is something that is workable or doable to the teams of people who will be asked to do that job in production. Not only do we have to mount that trailer hitch, but we also have to make sure that the trailer hitch is fastenable in there. So we took a proxy of that VR version of the tool that would be used to bolt that trailer hitch into place, and we proved to ourselves there's enough room to put that first fastener in. However, when we tried to use it to install to the second fastener, we see that the proposed tool that already exists in this brownfield assembly plant is not appropriate for fastening those hitches. So by using ESI Do Integrate, we already allow individual engineers to use their local installation of ESI Do to collaborate with each other remotely or perhaps in the same office location to see, is this going to be a good vehicle design in a good plant layout? If this vehicle is going to be assembled in multiple locations globally, then we might have the individual engineers from those production plants validate the proposed tooling and make sure that the tools that are engineered to work in one plant will still work in the other plants globally. With ESI Do Weave, we could potentially also use the latest cutting-edge XR hardware. In this case, we're wearing a Vario XR3 to validate the reachability of various components inside of a proposed manufacturing environment or subassembly cell for various parts within maybe a battery electric hybrid, a plug-in hybrid, and we want to make sure that people can reach what they want. So what you're witnessing here is somebody wearing a Vario XR3, and they're getting this mixed reality view of what they can see in the physical world and do in the physical world and what they can reach in the virtual world. Again, it's magical. It's time travel. We are propelling ourselves into the future to see what's it going to be like to try to assemble or try to build these various components, whether it's an electric vehicle, electric car, or it could be an electrified VTOL, vertical takeoff and landing aircraft. And by using this Vario in conjunction with my ICI Do Integrate or my ICI Do Build and Maintain, I get instantaneous feedback of what it's going to feel like personally for me to reach out with my hand and try to do that assembly, to try to hold these tools in my hand, and while standing in a virtual mock-up instead of a physical mock-up of the manufacturing environment, make sure that I can get my hand tools where they need to be to complete the subassembly, and make sure that the design and layout of my working environment is appropriate for the manufacturing process and the number of people and the number of engineering resources made available for completing that assembly. Here you see another example of us wearing that Vario XR3. In this case, I'm doing a service and maintenance validation, and I want to prove if this was a maintenance operation where I had to swap out some sort of a filter, swap out some cables or hoses within that assembly, that I'm able to do so. Now with ICI Do Build and Maintain, we can go one step further. Beyond just powering my own individual experience within that virtual world, I can capture that experience using this ergonomics mannequin. One of the challenges that we have with using VR to review this is that a lot of it is based on my own individual perception and what I feel, and is that comfortable for me? But that's not really quantifiable. So in this case, one of my colleagues is wearing a number of virtual reality tracking targets. And while wearing these virtual reality trackers, they're able to remap their own movements, their own behavior and viewpoint into a person of a different size and shape than themselves. And we can record those actions and we can validate, are those actions going to be comfortable based on any number of different standards and criteria for ergonomics. So in this case, we're showing RULA, the Rapid Upper Limb Assessment, to validate, are these considered comfortable or acceptable poses for workers to take day to day, run to run. And we're able to see, is this proposed tooling for my colleague right here? He happens to be around 6'4", and he's doing this assembly job, and the tooling might be perfectly suitable for him, and he finds it very comfortable to operate and very easy to grab and easy to control. But then if we were to put one of my other colleagues in there, somebody with a little bit shorter stature, with a little bit shorter reach, and maybe we would find that those tools are not in fact practical for that person to work in that environment. So whether we're talking about a installation of a spare tire into the back of the car, or we're talking about putting in the nuts and bolts that hold this vehicle together, we can make sure that we validate that people are able to fit and do the job. Within ICI Do, we have the capability to define an assembly process by performing a teardown, just manually disassembling it within ICI Do, recording that process and capturing the reverse of that teardown as the assembly process or order of operations. Now, if there's already a process proposed that has been captured and defined within your CAD or PLM system, it is possible to take that from, say, a MPM management tool like Windchill, or by recognizing from the imported data from other CAD or PLM systems any metadata or any other way that that data or that geometry has been notated as having a membership in a subassembly and a particular assembly. And we can bring that in to ICI Do, experience what it's like to perform those assembly processes, and decide whether or not we need to make adjustments or modifications to that proposed process. Then, as that proposed process plan matures and more is known about the layout of the assembly cell or what other logistics and working environment changes there are, we can again validate, is this a practical process for us to try to follow? And does it make sense for the amount of human movement we have to make going back and forth within this manufacturing environment, making measurements of where we place these logistics containers, and are they at an appropriate height and location to facilitate doing this job easily? So in this case, you can see on screen, this is a collaboration between two engineers who are validating that this two-person subassembly cell for these batteries going into perhaps a battery electric vehicle or perhaps a plug-in hybrid, we want to make sure that they can reach what they need to reach and perform the tasks and the jobs required to complete that assembly operation. And is this an ideal, is this a reasonable layout for that subassembly operation to deliver the expectations that we all have for production timing, for production rates, and make sure that we are, in fact, proposing a plausible, practical, and feasible, sustainable assembly operation for this product. As the vehicle program proceeds toward startup production and serial production and availability of that vehicle on the road, then we might have to convince our stakeholders that the project is in fact mature enough to advance to the next level of tooling ramp up, production ramp up, and fundamentally having this product out on the road. And so you can see on screen here a use of ICI-DO that we call collab, that allows us to have multiple users, anywhere between like 6 to 8 simultaneously emerged users walking around with wireless head-mounted displays, streaming ICI-DO from a remote cluster or server-side rendering engine, and allowing these multiple users to have their individual viewpoints, just as if we had teleported them in time and space to the future pilot plant or that future serial production plant to validate that our production plans are in fact feasible. As you can see, ICI-DO does span the entire vehicle development program, from maybe very early on engineering subsystems within the vehicle architecture to validate those assumptions or proposals that are made about vehicle topology. And we can do that on an individual engineering level quite early in the product development time cycle with the earlier data that we're able to achieve, all the way up through the preparation for the start of serial production, the ramp up of our production facilities, validating not only is our product well engineered, the production line, the products that we buy from other people that help us build our products, is well engineered and well planned as well. Well, thank you very much, and I look forward to answering any of your questions at the conclusion. Thank you.